Hey there guys, welcome to your Part 1 video notes for Chapter 1.3, which is going to be covering measurements and exact versus approximate values. Now we're going to start by going over upper and lower bounds. So upper and lower bounds refer to the interval in which an exact value lies. So usually the way we calculate that is upper and lower bounds are half a unit below and half a unit above a rounded value of a measurement. Now, usually, since it's going to be the same amount, so it's going to be half of the unit below and half of the unit above, what we're going to use this representation plus or minus. This means my exact value plus this value, so this value above, and then minus this value below. Now, really important, you have to be careful about this part here that says a rounded value of a measurement. If you're rounding to the nearest meter, you're rounding to the nearest whole number. So it won't always tell you you're rounding to the nearest whole number, but if you see to the nearest meter, to the nearest centimeter, to the nearest degree, you're rounding to whole numbers. So we're doing half of a unit, half of a whole number is 0.5. So that's where the 0.5 comes from, and plus or minus just accounts for my upper bound, which is plus, and my lower bound, which is minus. Now if you're rounding to tenths of a second, however, you're not going to use 0.5 again. Tenths of a second is represented by 0.1, and half of tenths of a second is 0.05. So in this case, my interval is going to be in increments of 0.05, above and below my exact value. Let's do some examples. So we have Jane, whose weight is 68 kilograms, to the nearest kilogram. So we're rounding to whole numbers, and we know half of a whole number is 0.5. So we're going to do plus or minus 0.5. Our exact value, they told us, was 68 kilograms. So we don't just leave it like this because it says determine the upper and lower bound. So they want us to explicitly say what is my upper and what is my lower. Now to find your upper bound, you're just going to take your exact value and add, that's where this plus comes from, this interval here. So 68 plus 0.5 is 68.5. To find your lower bound, you're just going to take your exact value and subtract this interval right here. So 68 minus 0.5 is 67.5. Those are your upper and lower bounds. Another example, we have Lewis's height, which is measured as 155 centimeters. Here's my exact value I'm going to be using, 155. Except this time, it's rounded to the nearest centimeter. So actually, it's the same. Since it's rounding to the nearest centimeter, we're still rounding to whole numbers. And half of a whole number is 0.5. So my interval is still 0.5. Now, when they say write the interval within which his exact height lies, do not just leave it like this. Although this does represent an interval, the wording says the interval within which his exact height lies. So what they want you to write it is interval notation using inequalities. So I'm using h to represent his height. Here is where my lower bound will go. Here's where my upper bound will go. 155 plus 0.5 is 155.5. And 155 minus 0.5 is 154.5. So be careful on how the question is being asked because it's going to determine how your answers look. If they just tell you to determine upper and lower bounds, you just have to find the two numbers. But if they specifically tell you to find the interval within which the height lies, then you have to write in inequality notation. Now, a third example is we have Marcos, who ran 100 meters in 11.3 seconds. His time is measured to the nearest tenth of a second, so we have to determine the upper and lower bounds of Marcos' running time. Now, notice here we have two values. We have to determine which one's the exact value we're going to be using. And to do that, we have to look at the question again. We have to determine the bounds of Marcos' running time. So we want the time that's related to time, or we want the number related to time, in which case it's the 11.3 seconds. So that is going to be my exact value, plus or minus, my interval. Now notice it's being measured to the nearest tenth of a second. So be careful, we're not going to do plus or minus 0.5, because remember, tenth of a second is 0.1, and half of 0.1 is 0.05. So this time, it's going to be plus or minus 0.05. Now it just tells to determine upper and lower bounds, so I just have to find my two numbers, 11.3 plus 0.05 is 11.35. 11.3 minus 0.35 is 11.25. My lower bound is here, my upper bound is here. Now, we're going to also go into measurement error. Measurement error refers to what happens when we're measuring. There's always going to be approximation, which leads to error in our measurement results. And the general formula is the difference between the exact value and the approximate value. So here it is in kind of a formula. I would write this down in your notes. Measurement error equals the approximate value, which is what the A stands for, minus the exact value, which is what the E stands for. So you're just subtracting these two values where approximate goes first, and then you subtract the exact value. Now, really important, measurement error is not a mistake. It's not always a mistake. Sometimes it has to deal with just the accuracy of the instrument you're using. For example, if you're using a ruler that only measures to centimeters versus a ruler that measures to centimeters and millimeters, the second ruler is going to be more accurate, where the first ruler is going to have more error just because it's less accurate. There is human error as well, so if you're not using the ruler correctly, if you're not aligning it, if you kind of have it at diagonal, you will get error. But just be aware, it's not always due to mistakes that humans make. Sometimes it depends on the instrument and how we're using the instrument. And also variability, this error, is inherent to any measurement process. So that's what's up here. Interestingly enough, flat earthers often point out the ranges of values, the error measurement results. They highlight things like words that we use, which are about and approximately, and say, hey, this is proof that science does not know things for certain. This is just a fundamental misconception of science and the use of numbers. So anytime we're measuring in science, we're not saying this is the exact value. Usually we're saying it's approximation, because error is part of measurement process and it can't be eliminated. Like I said before, there's different types of errors where it might be due to the instrument. So if it wasn't calibrated correctly, where you didn't reset it to 0, or it might be human error where a human might have messed up. But we can still get the average and figure out an interval by which our exact value lies within. Now let's practice. Now, as a reminder, if you didn't write it down, measurement error is my approximate value minus my exact value. So Carter measures a line to be 5.6 feet long. Since he's measuring, this is my approximate value. If the actual measurement is 6 feet, so this is my exact value. My bad, I meant to put approximate. Find Carter's measurement error. So if I know measurement error is my approximate value, which is 5.6, minus my exact value, which is 6, this is going to give me negative 0.4, which tells me his measurement is 0.4 below what it should be. Now, Alex measures a line to be 9.15 centimeters long. So here's his approximation. And the actual measurement is 9 centimeters, so here's the exact value. Find his measurement error. So we're going to do the approximation, which is 9.15, minus the exact, which is 9. That's going to give us 0.15. In this case, Alex overmeasured. He's 0.15 above what the exact value actually is. So sometimes your error can be below, and sometimes your error can be above. Depends. So here's other practice where it's a little bit harder, but that's IB for you. So we have a fraction 22/7, and it's often used as an approximation of pi. How close, in which we mean to how many decimal places, does 22/7 approximate to pi? Well, what you're going to do, and you're going to want to use a calculator for this, don't just round. Remember, this is our approximation, so that's our VA, and pi is going to be our exact value. And when we mean by pi, we mean the pi that the calculator uses, not just 3.14. 3.14 is an approximation. So I'm going to use pi as a symbol because I'm going to use that pi symbol that's inside my calculator that has an accurate or pretty accurate representation of pi. And if I do that, I'm going to get 0.001264. If you had put this in your calculator, you would see that you would also get this. And what we do is we say, okay, to figure out to how many decimal places is my approximation close to the actual value of pi, you look to see how many zeros you have. So in this case, looking at my decimal place, I have 2 zeros. So that means my approximation is close to 2 decimal places. Now the reason that happens is because 22 over 7, so if you do 22 divided by 7, you're going to get approximately 3.1428, blah, blah, blah. We know pi is 3.1415, blah, 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 blah. Notice the first two decimals are the same. 1414. Here is where they deviate. We get 2 and we get 1. So that's why we say it's close to 2 decimal places, because the first two decimals are similar. That's it. We're going to do more in class, and we're going to finish our Part 2 notes. Be ready for your skills check and more practice. If you have questions, feel free to send me a message or remind, sign up for tutoring, or message me on Canvas. Have a nice day.